What makes or breaks a voice pipeline is the response latency, how quickly the agent responds to what the human said. Now, there's several moving parts in the voice pipeline, and you have to locate where the latency bug is. And even after locating the many ways to fix it, many different ways to fix it. So as these voice agents evolve and more people are building it, I'm very curious on how people fix the latency bugs in industrial settings. Now, VAPI is one of the most popular voice assistant providers. You can build all kinds of customer agents or appointment agents on top of them. And there are a huge number of voice telephony cases and voice workflows that go through VAPI at this point. So I was really curious how they think about latency and how they fix these latency issues. And I found this very interesting article. This article talks at great length on how they go about maintaining a low latency across their platform for all sorts of agents. And it was a lot of engineering tricks and some cool math too. So let's dive in and see the details. This is a typical voice pipeline. The user audio goes into the ASR module, which feeds text into LLM. LLM output goes and does something, maybe function call, and then time TTS speaks, the bot talks back to you. Okay, so each of these modules have a latency, and together we want to optimize the total latency, which depends in turn on one of these modules. What matters is this response latency time. If from the time user says hello, how long does it take for the bot to say something, respond? And if this the conversational flow breaks when the latency exceeds 1200 milliseconds. 1.2 second is what they say, but that itself I think is a bit too long. 800 milliseconds is in general safe limit, acceptable limit. Okay, and if we manage to reduce this budget, then um, we can provide real-time feeding, real-time response. And then yes, if we save some on a particular module, we can spend more in another module, or say TTS, to get a better quality response. So there are these trade-offs. Now, what they observed is that bottleneck is almost always the LLM. So there are off-the-shelf optimized ASR and TTS services which operate in reasonable 300 millisecond, 400, but the LLM variance is huge, from 200 to 900, and this can make or break the real-time feeding. Okay, so LLMs can be implemented in a large number of ways. And you could pick different LLMs. You could try to fix it in many different ways. You could try to pick different LLMs of different reasoning capacity, say, and uh, the LLMs that are faster respond may not generate the most appropriate optimal responses. So fixing the LLM, even if they know that this needs to fix, is pretty complicated. Okay, so let's see how they fix that. First, it's good to discover that LLM is the bottleneck, and if we optimize this, we'll be in the safe range. And they spend a lot of effort trying to optimize it. And let's see how they go about doing that. The LLM providers advertise impressive speeds, but the benchmarks really hold up in production. So the first thing that they started is to monitor the latency across time. Okay, so the surprising fact is that the latency can vary drastically for every model, for every provider. So there's no way you can trust a provider to provide a constant or near constant latency. So this is GPT-4o varying over time. And there's even worse variation. Model that performs well on Friday night can be unusable on Monday morning. So that's really bad, and that's the core problem. This is the graph they say that they show to show the seriousness of the problem. So an LLM which is around 400 can go up to 1200 on a different time. So as this graph says, the obvious solution is to monitor different LLMs all throughout, and then at any point pick the LLM that has the lowest latency. So this problem of monitoring LLMs at scale while reducing cost, it's a quite tricky problem. And they spend several iterations. Attempt 1, go on to attempt 1, 2, 3, and 3. I think, yeah, it is really tricky to do this in an optimal way. And the core problem again is that you can't really rely on a request to a specific provider going through with 100% probability. You have to monitor and then route to the correct LLM. So obviously the brute force approach, send every request to all 40 plus OpenAI deployments and use the first one to respond. This is brute force optimal, definitely. You'll always get the least one, best latency here, but the costs 40x the tokens, which is not acceptable. We need a more smarter algorithm. Okay, so the what you can next do is smart polling at regular intervals. Okay, so every 10 minutes we poll for one token and consider that representative. So every 10 minutes, poll one token, get the latency, and switch to the one with the least latency. Okay, so this costs reasonable $400 per day, and the results, the fastest API is stored in Redis. The endpoint is stored in Redis, and anytime in the next 10 minutes, if we get a request, we use that. Okay, so this seems to work, but it gives rise to this graph where very quickly the accuracy of the best endpoint, best provider decreases in 10 minutes. So it's very hard to believe, but the latency changes so drastically that even within 10 minutes, the best latency provider may not remain. So we probably need more faster polling. But remember, we had the brute force solution. We can't just poll all of them randomly. Okay, so we need fresher data. Okay, so what do? We maintain a list like this um, uh, where the providers are ordered by their latency, and we monitor the last few, not all of them, but the top few. Anytime we find that the second one, it's like a heap. We monitor the closest one. Anytime find the list ordering to break, we switch the provider. Okay, so this seems to work. This is better than previous one. We don't rely on a particular provider for the whole 10 minutes. We can rotate by polling selectively, polling more polling, but selectively polling. So what's really happening is that we are exploring. There's a trade-off between explore and exploit. We can't explore everything. We explore. We can't explore everything at a fast interval. We need to. We also can't be very lazy in exploring. So I want to find some sweet spot that is in between. Okay, so this seems to work better. The problem is that we are stuck between the top few. They just say one, but suppose you explore the top few, you don't know if the rest of the 40, which ones of the rest of the 40 are faster, giving faster response in the 10-minute zone. So we need even more smarter strategy to explore. Okay, so with finite exploration constraints, you always get this dilemma, and this goes on. I mean, this isn't the final solution. There's more meat into it, but the overall idea is that instead of falling um, with these ad hoc lists or ad hoc sorted latency lists, you need to think about the distribution. So every provider has a distribution of latency. It goes from 300 millisecond to say 700 millisecond on the provider. So there's a probability distribution across um, the latency, which by enough monitoring you can discover. And so then you can exploit the properties of this distribution to actually find out where the uh, your polling order or the sorting order. Okay, so yeah, it goes on, and there are other problems that they discover that there's some calls that just hang. So it's behaving fine, but the best provider select just hangs, and that affects all of the rest of the uh, all of the rest of the queries in the until the refresh happens. Okay, so they start playing with um, detecting the spike happened on the best provider, and they set up a threshold. So if I've sent a request to the currently best provider and it doesn't respond within threshold amount of time, then I will send the same request to a second provider. That's a very nice trick. The question is how long to wait. Okay, how long to wait when you move from the sender. You don't want to send too many requests. If the first guy is going to respond with slight delay, you don't want to start a second request. It's going to cost more. Okay, so but the cases where it's really spike, it just doesn't respond or responds a long time, and it's good to just send a second response. The key issue is how long to wait until we know that the response is not going to go. And that's where the distribution comes in. If you know that the the latency distribution, the latency will roughly fall in this range, this provider. And what is the sigma for the distribution, assuming some sort of normal distribution. So if we have to wait for more than 2 sigma, then uh, then that means that we need to send a second request. And that this new strategy scales well. So you you send request to the first one, you know it's sigma, and if you don't hear within 2 sigma, you send it within the to the second one. Similarly, second one you don't hear within sigma. So this is very nice. You can extend all the way uh, to all the 40 providers in a demand-driven lazy manner. And hope is that much before you reach all of the providers, you'll get back a response in time. So this threshold depends very nicely on the distribution that you have monitored, and and so we have to do regular monitoring to keep the distribution updated and figure out the right sigma. So that's the crux of this solution. And so that's what it takes to make an off-the-shelf model like GPT-4o reliably fast, real-time voice. So like I said, there are several this pipeline. There are several possible bottlenecks, and they are in LLM just as this module. If they fix this, they'll be happy. But even fixing this required a huge amount of engineering work plus math. So 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 engineering and optimizing these voice agents is it's not at all easy. It, like there's one part about designing them effectively, thinking about the conversational UX, but there's a whole world about optimizing the latency. Yeah, so I hope this was useful and got a feel of how to optimize how VAPI optimizes the the pipelines.